So, welcome back friends. So, in the previous class we have been looking at special solutions of the Dirac equation. So, today we will continue that particular subject. So, before that let me just revise the kind of solutions we looked at as, in the last class. So, the first class of solutions we looked at is the massless limit of the Dirac equation. So, in 1928 when Dirac wrote his equation, soon after, within 2 years actually the massless limit was studied by Weil. So, these solutions are called the Weil solutions, okay, Weil solutions, or also a particular equation which becomes much simpler is called the Weil equation, which is also called the Weil equation. Now, this in the limit of the massless limit. So, what happens is we have seen it in the momentum space. The diagonal entries become 0. So, you can always have chi 1 chi 2 chi 1 chi 2 here as a 2 component Dirac spinors of the upper part and the lower part of the Dirac spinor. But now this comes completely decoupled, this becomes completely decoupled because you can always take a linear combination of chi 1 and chi 2 in terms of chi r and chi l. So, if I do that, so you have an equation purely in terms of chi r and an equation purely in terms of chi l given in this particular fashion. And now you immediately see that chi r and chi l are eigenstates of this particular operator sigma dot p by E or sigma dot p by mod p essentially, which is nothing but the helicity operator. So, the helicity operator is the projection of the spin operator in the direction of the momentum. So, the spin operator is nothing but the sigma is nothing but the spin operator, S is half sigma is nothing but the spin operator, which tells you what is the spin. This is same as in quantum mechanics, which I just imported back into relativistic regime of the quantum mechanics. Okay. So, the helicity operator tells you that what is the proper projection of the spin in the direction of the momentum. So, whilst fermions are eigenstates of the helicity operator, while fermions are the eigenstates of the helicity operator. Now, this is very nice, and we also looked at some important points about this. These are independent objects, these solutions are independent objects. These are 2 component spinors which do not talk to each other. You cannot convert a Weil spinor to another Weil spinor. So, a right handed Weil spinor cannot be converted into a left handed Weil spinor by going to a different frame of reference. This is not possible because Weil fermions travel with the speed of light. Now, if they do not travel with the speed of light, that means they are massive, then they are no longer eigenstates of the, they are no longer Weil fermions and they are no longer eigenstates of the helicity operator essentially. In those cases we use, for massive fermions we use chiral operators essentially, chirality operator which is 1 plus gamma phi by 2. This clarification between chirality and helicity was done in the last class. We looked into the great detail between the chirality and helicity, and I also told you the differences between Weil spinor and Dirac spinor. A Dirac spinor can be thought of as made up of 2 Weil spinors, say left moving and the right moving Weil spinor, okay, left handed and a right handed, or a left Weil spinor and a right Weil spinor. So, oh sorry, this somehow this is, I want to project on this particular case, yes. So, a left Weil spinor contains a particle which is moving in the opposite direction of the, whose spin is projection is in the opposite direction of the momentum direction, and it contains an anti particle which has, or a V solution which has parallel essentially which has spin which is projected parallel to the direction of momentum essentially, okay. And now chi r has the just opposite, essentially the particle which has parallel spin towards the direction of momentum and opposite spin to the direction of the momentum essentially. So, antiparticle which is in the direction of the momentum. So, the nomenclature left is always associated with the particle left handedness, not the antiparticle left handedness. Similarly, the right of the nomenclature for chi r is also identified with the right hand of the particle wave solution, not the antiparticle solution. So, these two are independent solutions and they form irreducible representations of the Lorentz group essentially. The Weil spinors of the Lorentz group. That means they cannot be further reduced further into some further representations, whereas a Dirac spinor can always be reduced in terms of two Weil spinors as shown above. Essentially, you can always write it as a direct sum of chi L and chi R. Now, any applications? Okay. Now, we have studied this Dirac Weil spinors. Are there any particles which are associated with Weil spinors? Now, for the case of Dirac spinor, we know the immediate application is electron. We have been talking about it right from the beginning. All the fermions and their antiparticles, okay, are which have mass form Dirac spinors essentially, which have mass. Say for example, electron, muon, tau, any of the fundamental particles, proton, neutron, any of these things all form Dirac spinors. Anything which has a mass, which has an antiparticle, which has opposite, which has spin half essentially all. Now, neutron, we will worry about neutron a little bit later. Neutron case is a bit complicated because it is uncharged. We will come back to it in this series of lectures, but anyway. Now, let us consider the case of a massless fermion. The massless fermion was first introduced in 1930s by Pauli. Okay. So, this was essentially around the same time as Weil had his equation. So, around the same time Weil had his equations, Pauli introduced something called a neutrino to explain theory of beta decay. Now, Fermi's theory of beta decay, Fermi's theory of beta decay was modeled after QED. Okay, it was modeled after QED. Now, we will see these equations meaning the QED Lagrangian, we have already seen it actually, but we will see in more greater detail later on. But Fermi's theory of beta decay is modeled after QED, which is also current interaction essentially, in which what is the process of a beta decay, you will see that a mother particle, say for example with an atomic weight A and an atomic number Z, goes back to another particle M prime with the same atomic weight, but the atomic number increases by 1 unit, emits a beta particle, beta minus particle. Now, underlying this, what is happening is a neutron is changing to a proton plus a neutrino essentially plus an electron. But this theory is not completely correct, because what they found was that if this is a two body decay, where if a neutron decays into a proton and an electron, if it converts into a proton and an electron, the experiment number the spectrum of the beta decay which goes in this particular fashion is not satisfied essentially. So, the beta decay spectrum, which is the energy of the electron, okay, and the number of events on the y axis, has a peculiar shape of this particular type, which is also sometimes called Curie plot. This is not exact, okay, the units are slightly different, and it has an endpoint energy which is something like here. Now, if it is a two body spectrum, this is not possible. This is what experimentally was found essentially. So, to avoid this, what Pauli introduced was another particle and an anti-neutrino of it, essentially it is called an anti-neutrino, anti-electron neutrino. So, he introduced another particle called neutrino, okay. He introduced another particle called a neutrino. So, in that case what happens is the energy distribution can be explained, because it is a three body decay, and so the energy distribution can be explained in this particular fashion. Okay. In the initial case, the electron takes up the minimum energy, and at the final case the electron takes up the maximum energy essentially in the final extreme of the plot of the essentially. So, this is very nice and good. So, this neutrino has to be introduced, and Pauli introduced it to be massless. So, it was completely massless. So, it was moving with the speed of light. So, this is where you have an example in nature where you have wild fermions essentially. So, you have fundamental particles which are wild fermions, and so neutrino is an example. A neutrino was considered to be a wild fermion for a long time. Now, as we will see later in the lecture that neutrinos no longer do not have this statement that the neutrinos are wild fermions is no longer true, because we now know experimentally that neutrinos have masses. So, if the neutrinos have masses, that means they are no longer wild fermions, and so you have to change your entire thing. They could be something else, okay. They could be something else which could be Dirac fermions, or they could be something else which we will see, which are called the Marronov fermions essentially. So, but they will not be any longer wild fermions essentially. So, wild fermions move with the speed of light, and they are always traveling. So, they are always left handed or right handed essentially given the choice. Okay. These are the only two choices. So, neutrinos were considered to be that, and this is the first example which we have seen in nature of a wild fermion. But the wild fermions are useful even today when dealing with many cases where we deal with massless fermions, and which may attain masses later on due to some other mechanism. Okay. So, that means that they do not originally have mass, but by for some reason they attain a mass essentially at later on. Okay. This can be due to interactions. So, you can imagine that the fermion is massless to begin with, but due to interactions it attains masses because of some radiative effects or something, essentially some radiative corrections, meaning like what we have seen for so the renormalization. Essentially when I talked about renormalization I was talking only about charge. Similarly you can also modify the mass of the particle and say because of the interactions we are feeling its mass, and its mass is getting generated because of interactions. So these cases are there essentially, and so while fermions are pretty useful even today when dealing with many cases, they are useful in various cases in field theory, maybe in for example in standard model and in standard model supersymmetric models or gravity or string theory or any of these cases you use Weyl fermions and as an and when required essentially. So, okay. So, to summarize, neutrinos are one of the first examples of fundamental particles which could be Weyl fermions. Even today they can be almost considered Weyl fermions. In the standard model of particle physics or fundamental physics, they are indeed Weyl fermions, but we have to go beyond the standard model to know that whether they have masses or not essentially. Okay. That is the story about Weyl fermions, and this is their equations and their solutions essentially. Okay. Now today a second class of solutions which are pretty interesting, again a connection with neutrinos will be considered, which is called Majorana fermions. Now when in the 1930s when neutrinos were considered, okay, people thought they are all mostly Weyl fermions. Neutrinos were Weyl fermions from 1930s all the way up to the standard model, building of the standard model, so 1960s 70s or so. Okay. But in 1933 there was an alternative approach which was neglected at that time, but which became very important in the recent times. In particle physics it started becoming important in the late 60s 70s and around the same times essentially. This was the solution of the Dirac equation which was found by Ettore Majorana or Majorana essentially, okay, in 1933. Okay. Now what was this the question Majorana asked essentially. The Majorana asked, you know the Dirac equation. So the Dirac equation is nothing but again or the Dirac Lagrangian or the Dirac equation is nothing but I slash del mu minus m psi, okay, and the Dirac Lagrangian would be I del slash minus m psi bar psi, okay. L Dirac equation is this, okay, I del slash. Now what Maron asked was that this has the condition on the gamma matrices, right? We were looking for the solutions for the gamma matrices. So he was asking the solutions, are there any solutions? So we had the solutions that gamma mu, gamma nu, g mu nu and other thing I also introduced you gamma mu, gamma 0, gamma nu, gamma 0 is the gamma nu dagger essentially. Okay. Now the what the question Majorana or Majorana asks is, are there any real solutions for this thing, meaning are there any real solutions for the Dirac equation. The reason why he wanted to ask it, that you know that in general the Klein-Gordon equation is a real equation essentially. Okay, the Klein-Gordon equation is a real equation. So he was interested to know if there is any place where psi can also be, the Dirac wave function can also be completely real, and if there are solutions for this particular case essentially. So like in Kj equation, not the complex one, which has real solutions. In fact, the complex one also can be considered as two real solutions. If I remember correctly, that the complex one can be decomposed into a real part and an imaginary part, and it can be written as two real solutions. Okay, so the Klein-Gordon equation can always have a real solution essentially. Are such real solutions? Possible for Kg equation, for Dirac equation. And the answer is yes, and Majorana has managed to find them. And these have an interesting quality, that the gamma matrices in this case are completely imaginary. Okay. So this is a breakthrough work which he has realized essentially. So suppose if your gamma matrices are completely imaginary, you will find a solution in which the wave function is real essentially. So for example, let me give you an example in which the gamma matrices satisfy, all of them are completely imaginary and they satisfy the Dirac equation. So let me call with a tilde, because I just wanted to make sure that this is called the Majorana representation. Now this is called the Majorana representation of the gamma matrices. Now you see sigma 2 is already imaginary, completely imaginary. So gamma 0 is given in terms of sigma 2, and also the gamma tilde and gamma 0 has opposite if it is off diagonal, okay, and okay. So the gamma 2 would have a minus sign. Only difference between gamma 2 and gamma 0 is a minus sign difference essentially, and in front of sigma 1 and sigma 3, which are both real matrices, and you see that I have put an I on the top in front of them essentially. So it is I sigma 1 and I sigma 1 forming gamma 1, and sigma 3 is forming gamma 3, which is I sigma 3 essentially. So you see that compared to the Dirac representation, which is completely off diagonal, in this case the gamma matrices are diagonal essentially, and only the gamma 2 is off diagonal. Now remember sigma 3 is a diagonal matrix, which so this gamma 3 will always be diagonal, and sigma 1 is off diagonal matrix 0 1 minus 1 0 0 1 1 0. So this will be an off diagonal part essentially on the 2 by 2 part and off diagonal 2 by 2 part essentially, whereas sigma 3 will be a completely diagonal matrix. This representation is called Majorana or Majorana representation. Now put this back into your Dirac equation, okay. Now put this back into your Dirac equation, and now what you will see is these are all purely imaginary, no. So you will see gamma mu tilde star is equal to minus gamma mu tilde. So the gamma mu star is minus gamma, it just picks up a minus sign essentially, you just pick up a minus sign. Now you put them back into your Dirac equation, you put them back into Dirac equation, okay. Putting them back into the Dirac equation, what you will see that psi tilde, the solution is nothing but psi tilde star. Psi tilde, the Majorana wave function, is nothing but its own is equal, it is a real solution essentially, it is a real solution, okay. So how do you see it? Just put it back into your and you will see these solutions are also allowed essentially, wherever psi is allowed and psi tilde is also a solution, psi tilde star is also a solution essentially. So when you put it back into the Dirac equation, which is written here, it is written here. So you put it back into the Dirac equation here, expand it, and you will see the solutions psi tilde is equal to psi tilde star are allowed essentially. But okay, good. So far so good. So these are real solutions of the Dirac equation. These are real solutions of the Dirac equation. So to summarize, if all the gamma matrices are imaginary, if all the gamma matrices are imaginary, you end up having real solutions of the Dirac equation, okay. And how do you get imaginary gamma matrices? You can think of one particular representation which I call as the gamma matrices representation, okay, and these are purely imaginary. completely imaginary because they are all I functions of I essentially, and in this case you end up having the wave functions of the Dirac equation psi is equal to psi star. So, this representation of the gamma matrices is called Majorana representation, and this gives you real wave functions. But now there are several lingering questions. Do you have several, this is very nice. So, what does it imply? What does psi is equal to psi star imply? Okay, and is this representation unique? Okay, so we have several these questions. Is this representation okay, is this representation unique? That is one of the first questions you have. So, what are the implications for the, what are the implications? If psi is equal to psi star, what does it mean? So, these are the questions we have which we will address in the coming lecture. Okay. So, I will stop here and we will continue this topic in the coming lectures. Thank you very much.